Hi everyone, I'm Mr. Bozade and welcome to another flip video. Today we're going to talk a little bit about torque and forces in equilibrium, and we're going to talk about those two things in the context of the classic physics sine problem. This is one of two kind of classic physics sine scenarios that you'll see. Why do we call it a sine scenario? Because it's kind of like the kind of thing you'd see at like a restaurant or something like that, where you've got a beam that's coming out and like there's a sign hanging off of it. So this mass that's hanging here is going to represent kind of like that sign. So how are we going to talk about this? Well, we're going to talk about this from the perspective of torque. One of the things that we've talked about is that torque is equal to force perpendicular times the radius. Or we can think of that as torque is equal to force times radius times sine theta. The important thing to note is that this angle theta is the angle between the force and the radius. So to give you a little perspective on that, like let's say this was our radius here, we could either do it this way, where we do radius times force perpendicular. If we think about the force of tension, which is at an angle, the component that's perpendicular, this times that radius. Or we can do it this way, where we do the total force times the radius times the angle between the radius and that force. So we'll look at it both perspectives. The other thing that we're going to bear in mind as we look at this problem is that equilibrium means that all the forces and all the torques are balanced on the object. So in the x direction, in the y direction, and trying to rotate it, all those things are balanced. I've got the kind of values from this problem listed up on the side of the whiteboard there. And the first thing you want to do when you want to try and solve a problem like this is you want to draw a free body diagram for the beam or the object, whatever that main focus is, whether it's a beam or an object. You want to draw the free body diagram for that. So I'll start by doing that, and one of the things that's a little different here from the past free body diagrams that we've drawn is well, you want to draw the forces now at the point that they're being applied. So, for example, the force of this hanging mass is being applied right here. So we'll call that force of gravity of that hanging mass. The force of tension is being applied right here. So we'll call that force of tension right there. The bar itself has some mass. Oops, that's okay. The bar itself has some mass, and it's being applied. We can imagine that the bar's mass is being applied right at its middle, right at its center of mass. So we can say that the force gravity of the bar is being applied right in the center there. Now, an interesting thing that people don't always recognize when you're looking at a sine problem is that the hinge is applying some forces in the x and the y direction. So, for example, when I do this, we can see that it's going to slide that way in the x direction. Why doesn't a hanging sign like this slide in the x direction? It doesn't slide because the hinge is providing a counter force to balance that out. Or it also wants to go in the y direction, right? So if I do this, we can see that it wants to slide down or fall down in the y direction. But the hinge is applying an upward y force as well. So something you don't often think about when you're looking at kind of a sign like this is that the hinge is applying a force in the y direction and a force in the x direction. So we'll draw those in here. We've got force hinge y and force hinge x. And those are all the forces that are acting on this side. I'm going to move this out of the way now so it's a little easier to see. We've got our diagram, and we're ready to rock and roll. Like I said, I've got all the values listed right there. So we're going to start by applying our understanding, our recognition that net torque is 0 because it's in equilibrium. So we'll go ahead and we'll do that. So we'll say net torque is equal to 0. Before we do that, we need to think about where we're going to put our axis of rotation. One way I like to approach that is I like to think about what things do we have values for. We do not know the value of that mass. We do not know the value of this force tension. We know the value of the mass of the bar, and we're given the value of the force of the hinge in the y direction, but we do not know the force of the hinge in the x direction. So if this is what we're trying to find, we do not want to put this axis of rotation where we're trying, at the point that, of the thing we're trying to find. So we're either going to put it here or here. And because we know that value, it's going to be in our best interest to put it right there. And you'll see why in a moment. So we're going to put our axis of rotation where force gravity of the hanging mass is located. Now let's dive in. This means add up all the torques that are acting on the beam or the bar. So we've got the torque of force gravity of the hanging mass. We've got the torque of force tension. Now notice, I'm not putting any pluses or minuses just yet, and I want to ask that you do the same thing. Hold off on putting your pluses and minuses in. We'll do that in a second. You got torque of force gravity of the bar right here. You got torque of force of the hinge in the x direction. You got torque of force of the hinge in the y direction. And those things all combine to equal 0 because it's not rotating clockwise or counterclockwise. Before we talk about clockwise and counterclockwise, let's think about which of these torques are 0. 2 of those torques are 0, and here they are. Here's the reason why. Torque of force gravity of the hanging mass is 0 because even though that force is perpendicular to the radius, it's at a distance of 0 from the radius. So that's going to be 0 because its radius is 0. The other force, or the other torque that's going to be 0, is the torque from force hinge x. So this is going to be 0, and the reason for that is because the radius goes this way, points that way, and the force hinge x points that way, and they are not perpendicular at all. So this is going to be 0 as well. Now we can take a minute and think about our pluses and minuses. Typically in physics, we say that the counterclockwise direction is the positive direction for torque, and the clockwise direction is the negative direction for torque. So if I pretend like this is my beam and that's my axis of rotation, then if I look at this force of tension, it's going to try and rotate it this way. It's kind of pulling up at an upward angle. It's going to try and rotate it that way, which is counterclockwise. So the torque of force tension is positive. On the other hand, if I look at this force gravity of the bar or the beam, it's trying to go like that. It's trying to torque it that way. It's trying to torque it like that way, which is clockwise. So that's going to be a negative force. And then force hinge y is trying to torque the beam this way, which is going that way around, which is counterclockwise. So that's going to be another positive torque. So let me rewrite this so it's a little bit more clean. What we're left with is plus torque of force tension minus torque of force gravity of the beam plus torque of force hinge y all combined to equal 0. Our goal, let me remind you, is to try and find the force of tension. So we'll start by finding the torque that force tension is applying. So we can say torque of force tension minus force gravity of the beam that is perpendicular to the radius plus force hinge in the y direction that is perpendicular to the radius times the radius, all combined to equal 0. Now, we can drop these perpendicular signs in our next step because both force gravity of the beam or the bar and force hinge y are completely perpendicular to the radius. So we don't have to really think too hard about that. So we can go and just simplify this and say torque of force tension minus, we'll say, mass of the beam times gravity times r plus force hinge y times r, all combined to equal 0. Number-wise, let's look at what numbers we put in there. So torque of force tension minus mass of the beam, which is 1.2 kilograms, times the acceleration of gravity, which is 9.8, times radius. So where is the mass of the beam or the bar, that force being applied? It's being applied right in the middle, which is half of the total length, which is 0.4 meters. So that radius is 0.4. Plus force of the hinge, which is given to be 7 newtons, times its location that's being applied at, which is all the way at the other end of the bar. So that's 0.8 meters, all combined to equal 0. I already calculated this out. What we find is that this comes out to be 0.896. So torque of force tension comes out to equal basically 0.9 Newton times meters. Okay, so that is the value that we find for not the force of tension, but the torque of force tension. Now, the question asks us to find the force of tension. So let's try and do that right here, knowing that the torque of force tension is 0.9 newtons times meters. So here's what we can do. I'm going to do it two ways. I'm first going to find that force of tension using torque from this perspective. Then I'm going to find that force of tension from torque of that perspective, and hopefully, well, we should see that they're the same thing. So we can say torque is equal to force perpendicular times radius. But we can also say that torque is equal to force times radius times sine of the angle between those two things. So we know that this is 20 degrees right here. And if I were to draw the part of this force, dotted line, that's perpendicular, the component of force tension that's perpendicular, that would be, I'd call that force tension y, and I'd call this force tension x. Well, the angle that this makes is 70 degrees. So if I want to think of torque from this perspective, force perpendicular times radius, then here's what I can say. I can say that the torque of the force of tension is equal to the part of force of tension, so force tension y times radius. And force tension y is equal to the hypotenuse of this, or total force tension, times cosine of 70. So I can say torque of force tension is equal to force tension times cosine of 70 degrees times that radius or that distance. And that radius or distance is going to be from here to here, so that's going to be just as a 0.1. It's given in the problem. If we plug all that in, we see that this is 0.9 Newton meters. Force tensions are unknown, times cosine of 70 degrees, times the radius, which is 0.1. We plug all that in, and we solve for it. We find that it's like 26.3 newtons. So the force of tension is 26.3 newtons is what we get for the force of tension. And that's not the perpendicular part. That is the total force of tension. Well, we should find the same thing over here. So we're going to say torque of force tension equals force tension times r times sine of theta. Now the angle here is going to be the angle between r, the radius, and the force. And so if we look at this, the radius is right here, and the force is right there, right? So the radius kind of points this way, and the force points that way. So the angle between those two is 20 degrees. So what we can do is we can say torque of force tension equals force tension times the radius, which we know is 0.1, and times sine of 20 degrees. And we know torque of force tension is 0.9 Newton meters. If we plug this in our calculator, lo and behold, it comes out to give us the same value. 26.3 newtons is our force of tension. So you can see that there's two ways that you can approach applying the torque equation, either by thinking of it as force perpendicular times radius, or as force total times the radius times sine of the angle between the force and the radius. So there you have it. We found one part of this problem. Now let's find the other parts. We found that the force of tension is 26.3 newtons. So we know that this guy is 26.3 newtons. Now, the other things we want to find is we want to find this mass, and we want to find the force of the hinge in the x direction. How are we going to do that? Well, we're going to do that by applying our other pieces of knowledge of equilibrium. We just applied our knowledge that net torque is 0, but what about that net force y is 0, net force x is 0? So let's dive into net force y. Net force y is also equal to 0 because this thing's in equilibrium. It's not, all the forces are balanced. So in the y direction, that's a number of forces. And again, as per usual, let's just say down is negative and up is positive. So negative force gravity of the mass plus force tension y minus force gravity of the bar plus force hinge in the y direction, all combined to equal 0. So let's see here. What we can look at is we can look at our knowns and unknowns. This is what we're trying to find. This is something we know, this is something we know, and that's something we know. So we can solve for that mass. We can write this as mg, negative mg, plus force tension y, which is going to be force tension times cosine of 70 degrees. That's this part, this component, the y component, minus force gravity of the bar, that's mg, right? And we know the mass of the bar and gravity is 9.8, plus force hinge, which we know is 7, all combined to equal 0. So this is our unknown, m times 9.8, plus force tension, which we found to be 26.3, times cosine of 70, minus mass of the bar, which is 1.2, times 9.8, plus 7, all combined equals 0. So you see mass is your only unknown, and when you plug that in, you discover that the mass, the hanging mass is 0.43 kilograms. So that hanging mass is 0.43 kilograms. And then, to find, so now we found 2 of the 3 things. We found this guy's mass, the force of tension, and then finally to find the force of the hinge in the x direction, we're going to apply this idea that net force in the x direction is 0 when things are in equilibrium. So let's go ahead and do that, and you'll find that this is probably the easiest step of it all. Net force in the x direction is 0. And per usual, we'll say to the right is positive and to the left is negative. So in the x direction, we've got force tension x, which is positive, and force hinge x, which is negative. So those 2 things are going to combine to equal 0, so we can go ahead and we can say negative force hinge x plus force tension x combined to equal 0. Force hinge x is what we're trying to find, so force, basically we can say force hinge x is equal to force tension x. They're balanced, so force hinge x is going to equal force tension times sine of 70 degrees. And we know force tension is 26.3 newtons, 26.3 newtons. Plug that all in your calculator, and you're going to find that force hinge x is equal to 9 newtons. So force hinge x equals 9 newtons. And there you have it. We've now solved for 3 things in the context of kind of a classic physics sign problem. And we did that by doing 2 things, or 3 things in some ways. We did that by using our knowledge of torque. We did that by using our knowledge of, in equilibrium, the net force in the x direction, the net force in the y direction, and the net torque all combined to equal 0. I hope you're able to follow that. Ask your teachers if you need any help. Ask me if you need any help. And see you soon.